just going to make a quick note before we start that it's great to be in an astrobiology conference because the background slides are going to go much more smoothly. I presented this at a microscopy conference a few months back, and it was a different experience. So thank you all for being here and being you. I'm going to talk, this is going to be a little bit of a pivot from some of the previous talks, but I'm going to talk about some of the methods that I've been working on to actually detect life on a mission, a life detection mission to Europa or Enceladus. I'm also going to make a note, so I'm going to be talking about life detection missions to Europa and Enceladus as a target for this, but once you have a space-capable microscope, this could potentially be applied to like all sorts of destinations. So there's lots of fun possibilities here. The aforementioned background slides. So when we're picking destinations to look for life, we like to look for places that have habitable conditions, things that have liquid water, abundant energy sources, and conditions that are suitable for life as we know it or as we might predict it may exist. And I'm just going to let Enceladus and Europa sit up there because we've already heard a lot of justifications as to why those are promising targets to find those conditions and why we might have had an origin of life or living organisms currently there. But when we're searching for life, we also have to think about how we're actually going to look for it. And so we can kind of break down life into some of the key components that make it up. Things like catalysts that help it metabolize, things like information storage polymers, so DNA or RNA and Earth-based life, but that might look very different for extraterrestrial life. And also compartments. Life on Earth, life as we know it, loves to put things inside of membranes. And then sometimes they put those membranes inside other membranes and have them connect to other even more membranes. But that packaging really helps it do some interesting chemistry. And so when we're then thinking about this in the context of a mission, we can start to think about how we might actually observe that and what analytical approaches we need to take to try and get at that. And so I put the giant table up here because these are all things that people are working on for life detection instrumentation. But we're going to be focusing for this talk on containers. And so the reason for that is that, again, as mentioned, life loves to package things into compartments, and those compartments can be directly observable by using a microscope to look for morphology and also for the colocalization of certain key chemical biomarkers. So in our team, we're working on a microscopy system that we call a luminescence imager for exploration or life. And there's two key hardware components of this system. One is the fluidic subsystem, and this is to deal with the actual sample processing and preparation for imaging something. So my background, full disclosure, is actually not in astrobiology. It's in fluorescence microscopy. And I spent like 5 or 6 years in grad school just moving fluids around in tubes and preparing things on slides before they actually get to the microscope. I've been told it would be expensive to send me to Enceladus. So this is my replacement. And then the other end is the actual microscope itself. So the optics system, which is going to have all of the things that you need to actually take your pretty pictures. So I'm going to break down what goes into these systems a little bit. So the fluidic subsystem, that silver plate on top, is the rotary filter stage. And so the stage can do 7 individual experiments. And so that accounts for, originally this was designed with the Europa lander mission concept in mind, where there would be 3 separate samples, each with a replicate and then a procedural blank. And then each of those individually has 3 filters of different sizes. And so that basically will let you sort out particles. So the filters are 10 microns, 1.2 microns, and 0.2 microns in size. And that's just so you don't end up with larger particles obscuring any of the smaller particles that you're trying to image in your sample. And that way you're not missing any of the like good stuff that might be there. It's also attached to the fluidics manifold, which is the part that actually moves all of the liquids and fluids around. And it also has a lot of sensors for pressure, pH, conductivity, and also crucially some storage for the fluorescent stains that I'm going to be talking about a little bit later in the talk. And then these were the filters that I mentioned earlier. And so this is, again, for sample size sorting. But they're also made of a silicon nitride substrate that has a low fluorescence background. And this whole system has passed environmental testing. So one thing about microscopes and also fluidics has a fair bit of spaceflight heritage, but in general, hardware can break. And I'm sure everyone who's worked in a lab has dealt with a lot of like issues before. So you want to make sure that these things are robust and you can actually get it to where you want to launch it to. The optics subsystem is a nice small compact box. And so this is a 10 centimeter by 10 centimeter by 13 centimeter cube. I have an image on my phone that I didn't upload to the presentation because the image quality is not that good, but for context, that's about as tall as a banana, which is very small for like a benchtop fluorescence microscope. There's like fancier microscopes can sometimes be like the size of a person if you're trying to do crazy like 2-photon lifetime imaging or something. But even an epifluorescence scope would probably occupy like this podium normally. And there'd be a lot of like miscellaneous kind of assorted parts. So it's a really nice little system. And so that contains all of the excitation LEDs, emission filters, all the optics. And so this table is just kind of going through what the different bits of hardware that we have are, and to kind of like give the high level summary of why this is relevant. Basically, we have 3 LEDs that are common excitation wavelengths for different fluorescent stains that can also excite different types of autofluorescence. And then one thing that's actually relatively unique to this microscope, certainly no microscopes I've worked with previously have had this, is the 275 nanometer LED. So that's actually fairly far in the ultraviolet range. And that's really good at exciting protein fluorescence. So tryptophan, phenylalanine, the various aromatic amino acid side chains actually fluoresce quite brightly in the ultraviolet. And so that can help image native fluorescence of samples and also excite the fluorescence of many different kinds of minerals. The objective is also set up to help, it's robust to spaceflight, but also the part that I think is super fun is that most objectives actually can't collect light in that ultraviolet range. So it is a custom objective that's built for those sorts of experiments. It has a piezo stage that lets us do automated Z-stacking. And this has also been subjected to environmental and shock and vibrational testing, and also radiation testing to the specifications of the Europa lander mission. So we're now on our ongoing work is actually characterizing this microscope by imaging different types of samples to see what the limits are of what we can detect. So this sample is just kind of showing some bright field images from a sample that was collected from Lake Untersee in Antarctica. And so I'm showing here the 10 micron and 1.2 micron filter just to kind of highlight that we can image the objects of very different sizes, and you can see the physical size of the little holes there. And so if we were to just put this all onto one filter, that microbial mat looking thing on the your left would probably obscure some of the smaller objects that we're seeing in the other filter sizes. And so As I mentioned earlier, we can also excite native fluorescence, and so we can correlate this as well with the bright field images. So we can take an image of an object, say, oh, hey, that looks interesting. I wonder what that is. Look at the native fluorescence in different ranges and get a sense of, okay, wait, we've got a bunch of like organics that are fluorescing in the UV range that are all localized on this object. That's pretty exciting. And then we can also then stain the sample with fluorescent stains to look for more specific chemical signatures. And so in this case, I'm showing the same sample after it's been treated with a stain for primary amines and another one that stains lipids. And so we can look for both the presence of those molecules, but also their co-localization in space. And this is a really like unique and powerful kind of data that you can get from the microscope, is not just like what compounds are there, but seeing that they're associating with each other kind of gives you a good piece of evidence that you might be seeing some disequilibrium and some living structures. Microscopy data is also large, maybe not as large as some of the types of data that we've talked about in this conference so far, but certainly large enough that if you were trying to send all of this data back from Europa or Enceladus, it would be more complicated to handle. And so one of the things that we're able to do on this microscope is actually take a Z-stack of images and compress it down to a single image that's much less in data volume. And so the image I'm showing right now is an image set of images that were automatically collected at different focal planes in the sample. And then after it's run through the compression routine, you end up with a single in-focus image, and you're now suddenly gone from megabytes of data to kilobytes of data. And then you can even go further with that, and you'll notice that this sample has bright objects against a dark background. We don't actually care what the photon shot noise is on the background. For our purposes, that might as well just all be zero. And so the final compression step is actually taking that and setting it to zero. And so we're just recording the actual bright objects that are detected in the image. And so that all reduces the data size quite substantially without really getting rid of any of the information that we actually want to take out of that sample. So how would this work in a mission? I just talked about a lot of different parts, and now I'm going to bring it all back together into how this system could be implemented. I have the little Europa lander picture there. But basically, we pretend that the microscope is somewhere in that lander. You would take your sample, process it, pump it through the fluidic system. You can image it on the microscope. You're going to end up with megabytes of data that you can then compress back down to your kilobytes of data, send it back to your ground-based observer that will then be able to say, oh, okay, cool. We got a microbial mat on Europa. Time to hit the press. And so, just briefly, acknowledgements. There's been a lot of funding that's gone into this. I'll be happy to take any questions.
Great talk. This is Chad Pozoriski at Georgia Tech. So I'm really happy that you touched on compression, first of all, of the data, because that's incredibly important. And I was also really thrilled that you talked about the sample prep and fluidics, because I think that's something that a lot of people don't consider for these in situ missions. My question has to do with comparing microscopy and staining with perhaps something like Raman or IR, where you could get information about at least functional groups of the organics present and co-locate things at, I imagine, similar resolution spatially, but you wouldn't need to include those processing steps. So would you advocate for a system that's, I guess, maybe not redundant, but has both of those features, or do you think one is better than the other? Or?
Yes, this is actually a super interesting discussion, and we can definitely also talk more about it at lunch, but the high level thing that I'm going to say is that you get you're going to have different pros and cons and get different types of data out of those techniques. So if you're doing, if you want to get spatially correlated Raman data, when you're building a microscope and you're trying to image something, unless you're using a super resolution technique, you're limited by diffraction in terms of like the resolution that you can get, and that is proportional to the wavelength that you're using. So when you start to get into like the IR, range and things like that, your spatial resolution starts to be more limited than it is in the optical range. The flip side is, you're right, you can get precise chemical information out without, adding labels. And so I think that definitely those are like in the perfect mission architecture, I think you'd do both. Unfortunately, it's unfortunate that we can't send all the instruments that we want out there, but like in my ideal world, I think that would be a powerful like correlative technique there, to kind of get a strong sense of what you're seeing in your sample. But yeah, great question.
Thanks.
Hey, it's Emily again. Thanks for an awesome talk. This is really exciting. So I was wondering what sample prep looks like in the rover or whatever, and what the capabilities are for that. So could you actually do like incubation experiments and then look at it with microscopy, or is it coming straight from the environment and going straight to the microscope?
Yeah, so it's the design that we had in mind for sample prep here, and when I say we, it's not us. This was kind of built around the Europa Lander specifications, but essentially you'd have a sample cup that would collect an ice sample and melt it down, and so that was kind of the initial like thoughts behind the design here. But the fluidics processing system can basically handle anything that's in a liquid state, but the assumption would be that it's a relatively unprocessed field sample. Relatively unprocessed because obviously if it's like ice or something and you're melting it down, you are still doing something to that sample.
Thanks.
Okay, we have time for one more question.
Hi, thank you for the great talk. My question is, maybe I missed that you mentioned, how are you going to differentiate any other particles from the living materials? Like, can you specifically stain genetic material or anything biological?
Yeah, so that's a great question, and so the goal here is to kind of pick up as many different breadcrumbs as we can to try and differentiate. And so you mentioned stains for genetic material. One of the stains that we would be launching with this is a stain for nucleic acids. Now, obviously, that would be really awesome if we found DNA on Europa or Enceladus, but it's kind of an open question whether we would. So the idea behind looking for something like the colocalization of amines and lipids is that gives you a more like agnostic idea of like, hey, that might be living material because you've got these, chemical signatures that are collocating. The other thing is, so one of our collaborators, actually the person who helped build the microscope, has some ongoing work characterizing the fluorescence of a wide library of minerals to get a sense of like what they would potentially look like on the microscope, so we can hopefully differentiate between that and things that might be a little bit more biological, both spectroscopically and then also, morphologically. So yeah, but great question.
Amazing. Thank you for the talk.